So in this video, we're exploring Frobenius method for a double root example. So in this example, we're solving the ordinary differential equation of this one. That's number 1. So as we can see, this is the example where we have an x in front of other y's. So this is not all the integer coefficient. So in this case, we employ the Frobenius method. Using Frobenius, we can rewrite the above equation as this, where this term corresponds to x times y double prime, and this is just equivalent of expanding all the other second and third terms in the original ordinary differential equations. So after rewriting them all in the term of m equal to 0, the summation signs, we will get 5 terms, and it goes to 0. And we can number this one as number 2. So we see that the smallest power in this is x to the power r minus 1 for m equal to 0 because m starts at 0. So in Frobenius method, we only care about the smallest power. So that's why we have, by regrouping the above terms, we have negative r times r minus 1 minus r bracket times a0 for m equal to 0 gives you 0. And this gives us the value of r squared equal to 0. So we get the double root of r equal to 0. So because we have a double root of r equal to 0, we know that we can now just get both solutions with r equal to 0, since both solutions have to be linearly independent. That's why we have to use reduction of orders to find 2 linearly independent solutions. So the first solution will be relatively easy by just setting r equal to 0 and equate the sum of the power. So if we rewrite the above equation in terms of s, we can get s times s minus 1 as minus s plus 1 as plus 1 plus 3s as minus s plus 1 as plus 1 plus as equal to 0. And if we regroup this and express as in terms of as plus 1, we realize that as plus 1 is exactly equal to as. This gives us that if we just set a0 to 1, then we can get the first solution, which is y1. y1 would just be summation of x to the power m from m to infinity. This sign can also be written as 1 over 1 minus x for absolute value of x less than 1 for convergence. So after getting the first solution, we can move on to get the second solution, which has to be linearly independent from this one. So the second solution, we can write it as y2 equals u times y1, which u would just be a coefficient that differentiates y1 from y2 and make it linearly independent. So here we use reduction of orders for the second solution. Because we know that u prime equals to y1 to the power negative 2 e to the negative power p dx, and we know that p can be calculated to be 3x minus 1 over x times x minus 1. So we can integrate this part separately for the ease of calculation, and we will get this value, negative 2 ln x minus 1 minus ln x. If we plug this value into this equation, we basically get u prime equals to 1 over x. Because we know u prime equals 1 over x, we can induct that u itself would just equal to ln x. And because y2 is a function of u and y1, so we can literally rewrite this as ln x times 1 over 1 minus x, which gives us the result of ln x over 1 minus x. So y1 and y2 are linearly independent, and those are the 2 solutions for this original ordinary differential equations.